Hey everyone, and welcome back to The Explainer. Today, we're diving into an absolutely fascinating, frankly game-changing development in the world of AI architecture. We're going to unpack a highly anticipated preprint. This is Archive Paper 2606.18273. The research team, led by Gyojin Han, has proposed just an incredibly elegant fix for large audio language models, or ALMs. If you've ever found yourself wondering why your AI can perfectly transcribe a speech, but then completely misses the heavy sarcasm in the speaker's voice, well, you are definitely in the right place. So, to really wrap our heads around the problem, let's just use a simple analogy. Think about reading a written transcript versus listening to the actual audio recording, right? If you just read a transcript of, say, a heated argument or maybe a beautiful piece of music, you get the raw data. The words are there. But you completely lose the emotion, the pitch, the rhythm, all that context. Current large audio AI models basically do exactly this. Because of how they're trained, they strip away those rich acoustic dimensions and treat incredibly vibrant, complex audio like a flat, lifeless text document. They literally lose the music. So here is our roadmap for today's explainer. We'll start with number 1, the acoustic bottleneck. Number 2, continuous audio thinking explained. Number 3, inside the inference pipeline. 4, benchmark performance gains. And finally, number 5, a developer deployment guide. Section 1, the acoustic bottleneck. Okay, so to understand the cure here, we first have to fully understand the disease. Why do our current highly advanced architectures fundamentally fail to hold on to these rich acoustic dimensions? Well, it comes down to a core contrast between the traditional baseline models and this new framework. In standard baseline models, the hidden states are progressively shaped for one specific goal, predicting the next text token. This creates what's called massive text alignment pressure. The network is basically forced to compress or just totally throw away any acoustic data that doesn't directly help it guess the next word. The CoAP framework, on the other hand, proposes a persistent signal approach. It maintains a continuous latent workspace, meaning the rich audio data is actually preserved. Let's think about what happens when audio features are shoved through a standard multimodal projector into a language backbone. Look at everything that just gets discarded. Phonetic detail, prosody, the actual rhythm and intonation of human speech, overlapping sound events, affect, which is emotion, and pitch. All of it just flattened out. This is exactly why current models might be incredible at direct raw transcription. But the second you ask them to, say, classify a music genre or detect subtle emotional shifts in a customer service call, they completely stumble. They simply lack the underlying resolution to distinguish between acoustic patterns that seem semantically similar but sound totally different. Section 2, continuous audio thinking explained. So, how exactly do we fix this structural flaw? Enter the continuous audio thinking framework. By definition, continuous audio thinking, or COAT, is a framework that equips these models with a continuous latent workspace. I want you to think of this workspace as a sort of cognitive scratch pad for the AI. Before the model even begins to generate a single word of text, this scratch pad allows it to organize and actually hear the full, rich acoustic spectrum. It stops treating audio as this fleeting, transient input stream that just passes through, and instead it anchors it as a persistent, foundational signal. Now, you might be wondering, how does the AI know what to actually keep on that scratch pad? This is the really clever part. The workspace isn't just randomly saving noise. It is actively grounded through distillation from specialized audio experts. The researchers use these expert models to provide auxiliary supervision targets. Basically, this forces the latent space to retain highly discriminative acoustic features. The model is specifically being taught exactly what matters in the sound wave long before it ever starts talking. Section 3, inside the inference pipeline. Let's open up the black box for a second. Let's look directly at the mechanics of the CoAT inference process. The framework essentially inserts a brand new step into the traditional pipeline. Step 1 is your standard audio feature extraction. Nothing new there. But instead of immediately projecting those embeddings straight into the language model's token space, Step 2 routes them through a dedicated thinking block. This block is what maintains that continuous latent representation we were just talking about. Finally, in Step 3, the model aligns this newly organized workspace with your prompt context and proceeds right into standard autoregressive decoding to generate the text. And here is the kicker: 0.
That is the exact number of autoregressive decoding tokens this framework adds over the baseline. Because the thinking block doesn't actually generate tokens itself, and the whole thing processes entirely within the initial single prefill phase, it adds 0 decoding latency. Literally none. For any engineers tuning in, this is a massive win. You get all that rich acoustic understanding, but you don't sacrifice your text generation speed whatsoever. The paper includes this really vital observation. Auxiliary supervision propagates from the thinking positions to the model's textual responses. Okay, what does that actually mean in plain English? It means the language model is actively learning to look back at that cognitive scratchpad while it generates its answers. It's not a detached, one-and-done process. The language backbone is actively relying on that preserved acoustic information to ground its predictions, word by word by word.
Section 4. Benchmark performance gains. Theory and clever architecture are always great. But in AI, we live and die by the hard numbers, right? To prove that this framework isn't just some fluke that only works on one highly specific model, the authors rigorously validated COAT across 3 very established architectures. They tested it on QN2 Audio, QN2.5 Omni 7B, and Audio Flamingo version 3. And this is huge because it proves the architectural pattern transfers incredibly well to totally different models, as long as they utilize a standard projector and language backbone setup. And the sheer breadth of these improvements is wild. We're not just seeing a tiny bump in one obscure niche area. By keeping the music and the emotion totally intact within that latent workspace, the model showed consistent, solid performance gains across audio reasoning, general audio understanding, music classification, and importantly, speech emotion recognition. It quite literally fixes the exact domains that have traditionally suffered the most from acoustic information loss. Section 5. Developer Deployment Guide. Let's shift gears from the academic side to a realistic briefing on what it takes to actually deploy this today. Let's break down the hardware and production implications. First up, inference latency. As we mentioned, it remains totally unchanged since it runs entirely in the prefill phase, which is absolutely critical for real-time audio analysis applications. Second, your memory footprint. Now, this will change slightly. While your KV cache stays identical to the baseline, the continuous latent workspace does add some activation memory during the prefill, so you'll just need to ensure your GPU VRAM can actually handle those additional latent dimensions. Third, compatibility is really high. The single prefill design means you can practically swap in the thinking block with fairly minimal code changes to your standard inference scripts. However, if you are planning to fine-tune this for your own use case, you really need to heed this stark warning from the researchers. The entire framework relies heavily on that expert distillation we talked about earlier. If you attempt standard supervised fine-tuning on a custom domain without utilizing an audio expert or a high-quality synthetic data pipeline for your distillation targets, you will actively degrade the latent workspace's acoustic retention. Basically, it'll forget how to hear properly. Finally, you do need to know that, at least as of this paper's release, COAT is an architectural pattern. It is not a simple drop-in library yet. There's no public GitHub repository or easy pip package attached at the moment. Developers are going to need to build the thinking block as a custom module directly into their own training loops. So definitely keep a close eye on the archive page and the author's Hugging Face profiles for future code drops. Which brings us to a final thought I want to leave you with today. By proving that we can actually save the lost signal without taxing our precious decoding speed, the COAT framework completely challenges the current status quo of data compression in AI. So the big question is this continuous latent workspace, this cognitive scratchpad, destined to become the brand new standard for how all future AI models process not just audio, but the entire physical world? It is a fascinating question to ponder. Thanks so much for learning with us today, and we'll catch you on the next explainer.